In this class, we're going to work an example of an initial value problem for a first order linear differential equation. We're going to solve this using an integrating factor. So remember that when we're solving initial value problems, we're working all the way to the general solution, but then going a little bit further to identify the C value. And that C value is tied into the initial conditions. So the initial conditions can be presented in different ways. They're also called boundary conditions or initial values, all means the same thing. And they are tied into the C value. In other words, they are the numbers, 1 and 1 in this case, which are going to help us to find the C value. So when you find the general solution to a differential equation, you're actually finding a family of solutions, infinitely many solutions. Each of those makes a curve. The solution curves, well, only one of those is going to pass through the point we're interested in, which in this case is the point 1, 1. So remember, these boundary conditions can be written in different ways. This is effectively telling us that the solution curve has to pass through 1, 1. Sometimes you'll see it written as things like, say, f of 1 equals 1, or even like this, y of 1 equals 1. So different ways of presenting it. But basically that part comes at the end. That's just a little bit of numeracy to help us pin down the particular solution. So the main part, I should say, of the work in here is nothing to do with the boundary conditions. It's to do with whatever method we need to use to solve whatever type of differential equation we've got. So this is a differential equation in which we can use an integrating factor. So let's just work that up. So is it in the correct format? That's the first thing we've always got to check. Remember, the format we're looking for this type of equation is that the first derivative, dy dx, is on its own, and then we've got some function, let's call it p of x, multiplied to y, and then on the other side of the equation we've got some other function of x. So we do not have that format yet. But we can manipulate our equation into that format just by dividing through by x. So if you divide this term here by x, you're just going to be left with dy dx. If we divide the next term by x, we could write that as 2 over x. This term here, 2 over x multiplied to y, and then on the right hand side we just get e to the x over x. So we can see that this does now match the format. If we say that our p of x is the function 2 over x, then we've got exactly the format we need. So this is an equation in which we can use an integrating factor to help us solve it. So we can just go ahead now and define our integrating factor. I'm just going to work that over here. So we're saying that our p of x function is 2 over x. Our integrating factor then is e to the integral of the p of x function, 2 over x, integrating that dx. So we've kind of seen these, I think, already if you've been watching some of the videos, in the sense that quite often this integral here will have an x term on the denominator of a fraction. I'm just going to pull the 2 in front actually to make this 2 times the integral of 1 over x dx, just to make it explicitly clear that we're dealing with the integral of 1 over x, which is a well-known integral, and that integrates to ln x. So this is going to become e to the power of 2 ln x, and after a little bit of log work and simplification, which you should be fine with, that should come out to be x squared. So x squared is our integrating factor. Remember, the whole point of that is to then take that integrating factor and multiply through the equation by it. If you multiply through the equation by it, then you're going to get x squared times dy dx. You don't necessarily need this line of working, by the way, but I'm just going to put it in anyway. So we would then get 2x squared over x times y equals x squared e to the x over x. We can see that some of these terms can be simplified. So the first term is fine. We're just going to leave that. So that's x squared times dy dx. The next term we can divide top and bottom by x to give us just 2x times y. And then on the right hand side we can divide top and bottom by x just to leave us with x e to the x. But we know that the whole point of multiplying through by the integrating factor, the whole method here, is such that when we do that, the terms we get here can then be compacted into the derivative with respect to x of the integrating factor, so derivative with respect to x, of the integrating factor, which was x squared, whatever your integrating factor is, times y. So that's why I'm saying you don't necessarily need these lines of work, and you can basically go from here to your integrating factor straight to this line here, but it's up to you, and it's good just to put them in, I think, to show kind of the process we're going through. You can check that this and this are the same thing by using the product rule, the differentiation product rule. If you use a product rule on x squared y, you will find that it comes out to be that there, and that always happens in this, as you know. Hopefully you already know that, and that's just how the method works. The right hand side we're not changing, we're just leaving that as x e to the x. Okay, I'm just going to pull my working up here just to make some space. So remember, now we want to integrate both sides. If we integrate the left hand side, that just cancels out the derivative. So we're just left with x squared y. The right hand side is going to be the integral of x e to the x dx. Now in this particular problem, this is not always going to happen, but in this particular initial value problem, to integrate this here, which is a product of functions, we need to use integration by parts. Integration by parts, remember, is a separate technique, not an easy technique, but something which if you've not used in a while, it's not trivial, so you might need to review that. You can check out another video on that in Calculus 2. I'm not going to go into detail in this class as to how that works. I'll leave you to figure that out, but just to work up the integration by parts, so we need to define a u and a dv. So hopefully you know what I'm talking about here. If not, if this is all just crazy, then check out that video on integration by parts, work a few examples, and then maybe come back to this problem. I'm going to let my u equal x. That means that my du dx equals 1, and that basically implies that du equals dx. Hopefully this is jogging some memories. I'm going to define then my other term as e to the x, and that's going to be our dv. So dv equals e to the x. That means that if you integrate both sides, you're going to get v equals the integral of e to the x, which is still e to the x. So these are the things we need to use integration by parts. And remember, the integration by parts, the solution is uv minus the integral of v du. Or there's other ways to write it. That's one of the ways in which we can write that, or whichever method you're familiar with yourself. Okay, so the left-hand side here is not going to change. We're going to leave that as x squared y. Then we're going to use integration by parts on this, which is what I've started working up. So we need uv, which is x e to the x. This is the solution for the integration by parts, minus the integral of v. V is e to the x, du, which is dx. Okay, so basically a bit of substitution there. How does this help? Well, it helps because we can now go ahead and integrate that. The integral of e to the x is just conveniently e to the x. Okay, and then we've got our constant of integration on the end. So we're almost done at this point. We've got an implicit solution to our equation. We can make it explicit, in other words, y equals, just by dividing through by x squared. So if you divide this term by x squared, you're going to end up with e to the x over x. If you divide this term by x squared, you're going to end up with e to the x over x squared. And then the final term, you'd end up with c over x squared. So this is the general solution for this differential equation, written in an explicit form, but the c value is arbitrary. In other words, it could be whatever you want. So this is generating infinitely many solution curves. We only want one particular solution. So initial value problems have a particular solution, one solution. Of all of those curves, for every single c value you could ever conceive, there's only one c value that will give you a curve that passes through the point 1, 1. And that is the c value that we are trying now to identify. So really this is just a little bit of numeracy. We're just substituting in x and y as 1. It happens to be in this question they're both 1. They can be any numbers. Quite often one of them at least, if not both, have a 1 or a 0 or something like that. So we're just basically substituting. So we're going to substitute x equals 1 and y equals 1. So put in a 1 here for y. If you look at the way these terms are, so dividing by 1 squared or 1 squared doesn't do anything, so those denominators disappear. E to the power of 1 is just e. E to the power of 1 is just e again. And then we've got a c divided by 1 squared, which is just c, like this. These guys cancel. E minus e is 0. And we basically just get that c equals 1. So going back then from our general solution to our particular solution by subbing in the c equals 1, so our final solution here is that y equals, just going to basically copy this line, so we get e to the x over x. It's quite a complex solution, quite a complex function that's popped out as our solution here. And then we're just subbing in the 1 here for the c value, so we get plus 1 over x squared. So that is an explicit solution. It's written as y equals some function of x, so it's explicit, not implicit. And also we've now got the particular solution. In other words, if you were to graph this function's curve, then the curve would pass through the point 1, 1. Whereas if you make up different c values here and then graph those, then you would get curves that look like this one, but they don't pass through the point 1, 1. The particular solution always passes through the boundary or initial conditions given in the question. So you can see that the vast majority of work for this question, okay, this one happened to have integration by parts, but the vast majority of the work is just using the method to solve this type of differential equation. It's got very little to do with the boundary conditions until the very end. The boundary conditions are really just an added piece of numeracy to help identify the c value and to therefore help identify the particular curve, the particular solution that passes through the boundary condition point. So initial values are everywhere in differential equations. It's not like they need a technique in and of themselves. You learn the technique that finds the general solution for a type of differential equation, and then you just go a little bit further and to find the c value associated with particular solutions. So don't think that particular solutions or initial value problems need a separate technique. They're just the same technique, but just a little bit more working. So definitely worth spending some time working practice questions, both for this type of differential equation, both general solutions and initial value problems like this one, to find particular solutions.